Now we will see various search tree algorithms that are used to find the various strings. So in this regard, we can see we will discuss the next leaf algorithm, all leaf, and pre-order algorithms. So in the next leaf algorithms, it is a very natural form of algorithm, and it counts as we count in our daily life. So it is a type of counting algorithm, and in this algorithms consider Elmer A1 to the end of the last alphabet in the Elmer, and it then jumps to the next Elmer. So it's jumps from one Elmer to the next Elmer and counts the various strings. So this is the first algorithm, next leaf algorithm, in which A, L, K, and we will consider, and A is the element of Elmers, L is the Elmer, size of the Elmer, and K is the number of elements within the Elmers. So it will start from the for loop, and I is designated as L to 1. For example, in case of DNA, we can say that it could be 4 to 1. So we have to write the smallest digit at the end. It will change one by one. First will change first, and then second, then third, and fourth. So that's why we written in the order of 4 to 1. So again, next if loop will start, and it says that AI should be less than K, and if it is less than K, then AI is designated as AI plus 1. So it means that if the length of the Elmer is 8 and the elements within the Elmer is 6, then it will move and add one position and will become 7. Again it will move and the 8th element will come in that position, and so on until it will be equal or larger than K. And if it is larger than K, then AI will be considered as 1, and we will get the answer A. So in this case, we will find the different possibilities of the strings. So the next algorithm is the all leaves algorithm. L and K. L is the number of Elmers, and K is the K-mers, means the number of nucleotides. So A is starting from 1 to 1. We have seen in the previous slides that it various possibilities. So it will start from 1 to all the 1. So while loop will start forever. It seems that it will be the loop forever, and it will continue to compute at step number 2, but it is not the case. And we will see that when it will compute, will finish, we will get the output A. But it will, if it is not A is not assigned A 1 1, then the next leaf will be applied. We have seen in the previous algorithm, next leaf will apply here, and it will compute just like the next leaf. So we will get the answer when this loop will be applied here, and this will not be stopped here, and it will continue until we will get the answer at step number 6. So the computer scientists, they often represent all the Elmers as the leaves of a tree, as we can see in this figure. So this is the root of the tree, and in each step these are the leaves of a tree. So the scientists consider it as the leaves of a tree. So Elmer trees will have L level. So we can see this is a 1 level, L minus 1. This is the second level, L minus 2, and so on. So every tree has its L levels. So when we will add the leaves of a tree, the level will become L-1, 2, L-3 and so on. For example, the vertices at the third level, L-3, we can see there are 8 vertices. So these are called vertices, vertex. So these are different vertices. And this line is called the edge of a tree. So if we see the third level of the tree, we can see 1, 2, 3, 4, 5, 6, 7 and 8 vertices. At the second level we can see 4 vertices, and we can see there is a number written in each of the vertices. So we can find the different vertices at different levels. So the tree we can see here has 4 mer and k is equal to 2, and if we calculate all the vertices from level 1 to level 4, it comes out to be 31 vertices. So we can also say that in this tree with L levels and k childrens per vertex, so it means that these are the children per vertex. So we can also say that every level has a different number of children also. And the first one, it is generally called as the root of the tree. So if we make the figure upside down, the root will come in this position. Then we can clearly see that it will assume the shape of a tree. But in this diagram, we have to take the root on the top position. So we will consider all of these representation to be equivalent. Internal vertices, on the other hand, can be represented as a pair of items, a list of A of length L and an integer I that specify the vertex level. So we can see here that there are only 2 choices here. The k is 2, 1 and 2, and L is 4, means we have a strings comprises of only 4 elements of 1 and 2. So if we see here, we can see it starts from root, and the only choice we have 1 and the other we have 2, 1 and 2. And that in the first level we have only 1 and 2 here. Then this again divide into this level divide into 1 and 2. So if we divide it into 1 and 2, it will again comprises of 1 and plus 1. It will be 1 and 1. And in this position 1 we will add a 2, it will become 1 and 2. And so on, we will add again in this vertex 1 and 2, it will become 1, 1, 1 and 1, 2. So if we'll read this tree, it is very simple to read it. Here we can see it starts from root, it divided into 1 and 2, and if we go along the leaves of the tree, we see that it's a 1, we see it is 1, 1, 1, 1, 1 and 1. And if we read this one, we will see 1, 1, 1 and 2. So 1, 1, 1 and 2. So if we read this one, so it will start from 1, 2, 2 and 2. So it will be 1, 1, 2 and 2. So if we will read this one, so it will start from 2, 1, 2, 2. So it will be 2, 1, 2, 2. So we can come up with the level number 4. So each level has a different string pattern, and all of the patterns will be composed of k is equal to 2 and the number of string is L is equal to 4.